Hello to viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about the future of x86. So let's dive deep into it. So before we dive deeper into it, we have to understand what the hell is ISA. ISA in simplest term is basically how the heck binary bits, basically that on off switching thing, that's how they are arranged. Basically that's the grammar of it. So in the early days, basically just after Apollo mission, computers were a thing. People were building a thing known as computer. But at this point in time, everything was proprietary as hell. Basically, everything was custom. If you go to IBM, they had their own. If you go to anything else, Motorola, they had their own. So everybody built their own hardware and their instruction set architecture, meaning it was completely custom. It was not like, okay, we have this ISA, multiple people are building it. No, so there was no thing known as compatibility. Like that was not invented yet. So fundamentally, there were a few big successes. For example, IBM systems were quite successful. DEC PDP-11 was also successful. Another one you may have known it, Motorola 68000 used by Apple. So a lot of things were there, but nothing was like intercompatible and big thing. So it was just like, very small niche island, so to say. And systems were built end to end by just one thing. And there is a very simple reality of it. You would not get a lot of software in the computers, even though the horsepower was there. Like as in like a normal compute job, it can be easily done. It's just that there were not many applications. Why there were not that many applications? Because you had to literally find the people who are using it. For example, you're like, let's say you built an aeronautics calculation, this Boeing, which computer they are using? Are they using Motorola computer? Then write the software for them and hope they buy it. Or if they are using IBM, write the software for IBM, hope they buy it. So you can see that like there was not that much growth, even though the hardware, basically the foundation was already laid down. So things change. This happened. Intel 8086. So 8086 was released in 1978. Now IBM was growing, but they were like, you know what? We were not gonna go beyond a certain point unless a lot more people start to use it. And they were thinking like going from uber hyper business class people to like bit lower, like let's say middle management, things of this nature, basically, or even maybe customer also. So they started a new trend, so to say, and that trend started with IBM PC. So PC being personal computer. That puppy started in 1981 and they utilized that. And IBM was a very big corporation at this point in time, like daddy at this point in time, and Intel was scrappy startups. So they're like, yeah, we liked your stuff, we tested it, it's cool, it's GG, but you're just a small startup company. We can't risk multi-billion pipeline for you. You have to give us a second source. Meaning, for example, let's just say I'm building a fan controller. Let's just say I actually want to make this into a product. I will never rely on, this MOSFET. Let's just say this MOSFET is from one brand. I will always have a second source. Like if this MOSFET gets kaput or the supplier craps out, no problem, I can switch to something else. So the bigger the investment, the more second supplier you will seek. And IBM was risking a big enough money, so they were like, hey, we have to have this. And Intel agreed to it. That's why AMD is the only other company that can make legal x86 copies. Because the idea was two independent companies, the likelihood of both of them going kaput at the same time is zero. So that's why AMD got involved into it. And then rest is history, as they say. So it dominated. There was nothing else. Like how quickly x86 went from a thing that this new startup was doing known as Intel to, oh damn, this is the thing, to like, holy damn, this is the only thing. That happened very quickly because IBM built a personal computer with off-the-shelf part. For example, all this thing you see, and you were like, okay, dip packages and all that, because again, this time people were building silicons, but building your own custom silicons were ludicrously expensive. That's why you must have seen people talking about like old supercomputers were like, you have to make the silicon. Yeah, they were trying something different to keep the cost down. And again, this is the same logic Apple company also used, where it's like making their own system, where it's like, do not try to buy everything custom and all that. Just tada it from off-the-shelf part. Basically, if this video decoding chip is already used in let's say media equipments like cameras, teleprompters, so things of this nature, use that. If this is used for VCR decoding, use that. Everything was copy-paste from each other's thing, so to say. So they built this off-the-shelf part, and to make sure that people can develop for this, they made the manual open source, so to say. Not manual would be correct term. It's like how the heck our system reacts based on the command you tell it. It's like if you type this, it will do this. There was a giant instruction manual of that, and yes, like thick instruction. This is before CDs became cheap enough. So that time they actually used to print it out, and it was like big, thick documentation of it. And they wanted everybody to develop software for this, because they knew very early on, if there were no software, nobody will buy this hardware. So they're like, okay, cool. We're gonna make this instruction manual. Any Tom, Dick, and Harry can read the manual, develop the software for it, and have a fun with it. And again, it will be cheap enough. They can actually buy it and test it also. So cool, awesome. They released it. And that was the IBM PC's BIOS. So everything is cool, awesome, GG. But there was this tiny company, you may have heard of it, Compact. They looked into it and it's like, hey, we can invert it. The idea was, this manual is the translation layer between the software developer and the hardware. And it's like, okay, I do not have their hardware. What if I replaced my hardware and behaved exactly like that? So they inverted it, developed their own system, and it was PC compatible. And IBM reached into the market, some success. Compact reached into market, massive success. A lot of other clones came into the market, uber success. And here's the deal, this is when x86 started to grow. Users started to come in, and it developed the first successful app ecosystem. Now, I do not mean modern app ecosystem, how you're thinking when you're talking about iPhones. App ecosystem meaning there were people building softwares for this thing, knowing full well that there will be customers for it. It was not like, okay, you hire this software company to develop aeronautical software for your engine. No, they are just developing aeronautical software. They know somebody will buy it. So that app ecosystem, basically people making money, became a thing. And that created a scenario where it's like, hey, I want to do this thing. Let's buy a computer, let's buy a PC. And that created a feedback loop. So users were there, that created more software system, more users got into it. And because the user base was huge, and it was not locked to IBM only, because IBM, while it was very good and professional people used it, a lot of other people also jumped into it simply because Compact was cheaper and other clones were even cheaper. So that created exponential user market. That created exponential growth in clone software market. Based on that, people were like, hey, what if you could place those games in this sort of cheaper computer? So that created a feedback loop. That created even more clones, more competition, even more users, more adoption, and x86 became a god at that point in time. Flat out in 1990s, there is x86 and everything else. Like the end. There is no discussion at this point in time. And only Intel and AMD could build a legal ISA instruction set systems, because be mindful, if you know how x86 behaves, you can reverse engineer it and it will work. And again, that's the exact same thing Compact did. So it could have been done, but there are some legal missiles that will be fired at you. China did had a company that was trying to make an actual x86 clone, but the missile was fired. So they're like, nope. And complex instruction set architecture, basically CISC, CISC was the core of it. Now you have to understand, when this was built, this is long ago, okay? This is long ago, basically when floppies used to be 5 inches long, diagonal, so to say. So this is long ago. What does that mean? That simply means they were gambling. When Intel was developing that architecture, they were gambling. So their gambling was, future RAM would be very expensive and CPU would be very expensive. That was the reality there, and that's what they extrapolated, that in future also RAMs and CPU would be expensive. So to get the most out of it, we have to create a different language feel to it, basically much bigger complex instruction. But benefit of that, less RAM would be required and less clock cycles would be required, but you can do more with it. For example, if you will send one instruction, but it will do memory load, addition and store all in one call, which again completely invert to RISC architecture. RISC architecture reduces, like, bro, call data, add data, save data. Here is like one signal, one command, tada. So fundamentally, this became the dominant thing, and everything that you and I hold dear today happened because of this. Although ironically, IBM was the biggest loser in this. Basically, that I'm like, I really feel like IBM would be like, we created the manual, so we became rich, but we died. But such is life. So domination did happen, and clones literally made it real thing, and rest is history. Although if x86 was that great, then what the hell happened? How the heck downfall happened? So downfall happened simply because the core logic of CISC was no longer holding true. It's almost like, the companies back in the old days were like, okay, we're going to put a lot of effort into making small sensor basically cameras simply because sensors would be expensive. Sensors are not expensive. SoC is the expensive part now. So it happens. Sometimes you play a guess and it's like it flips. So they're the same thing. RAM became cheaper. Basically, you could literally have IBM's first generation system where like kilobytes of RAM, like whoa. To 1990s, your Casio having like 2 to 3 megabytes of RAM. So like that happened exponentially quicker. They were like, it's gonna get cheaper to like, and CPU got idiotically faster, meaning like it just like, whoa, like kilohertz to megahertz to gigahertz, and in less than human lifespan, not even lifespan, in 30 years, so to say, all this happened. So fundamentally that gamble on CISC was like, what the hell? So that happened. That inherently created this, like, we get it, why you created it, but it's feeling outdated because the core architecture, core philosophy was not that great. And again, even CISC could do awesome things if they were competition. They were no competition. Now you're like, wasn't AMD there? AMD only became really genuinely useful after Zen architecture finally started to get some traction. Before that, it was like horrendous. I have AMD Bulldozer. Let me put it this way, not good. So fundamentally, and this was for decades. Let the AMD and Intel started at the same time. And again, there were some court battles and all that also. But AMD took way too long to become a genuine competitor. So there was serious lack of competition, and Intel for decades were like, x86 is the daddy, so like, why care? It's like, and that was like, you know, the meme 14 plus, 14 plus plus plus, that meme happened. So the lack of competitor made them sloppy. They could have easily made CISC even more better, because again, the CPU is now far more powerful. The RAM is numerous. So what if you upgraded it to flex more of it? They did not do. And the backwards compatibility that allowed them to have this sort of market penetration started to become a liability, because again, people were changing. Like, you have to understand, what was logical in 1990s is no longer logical today. It's almost like expecting SATA SSD to behave as fast as NVMe SSD. It won't. Fundamentally, we had to change. So all the x86 protocols, the system that is embedded into it is no longer like, you know, yo, it's like, we have to carry this, like, you know, hold the luggage of past. And that created a bloated library. All of these things directly started to play a role, which again, people did notice that things are not looking as great. And then we come to the RISC. RISC, now be mindful, it also started exactly the same time. These people bet on the fact that RAM and CPU will become cheaper. So ARM2 was released in 1987, the first commercial, so to say, ARM product, so to say. And by 1990s, again, they were never as successful in computer environment, but they were very successful as microcontroller and small processing units. So like, your washing machine could have had ARM. So 1990 comes around, and they create a spin-off, a new company, what we call Arms Holding right now. So for commercial licensing. Now, same way IBM wanted other companies to utilize their product, this company went one extra step. It's like, just make the damn thing. I do not want to deal with it. Just give us the licensing fee. They removed themselves from the equation. It's like, we're going to make things, we're going to make the, what you call, base architecture. We're going to have some profit. If you want to go YOLO on it, go YOLO on it. And there were other companies also. They were experimenting with RISC, reduced instruction set compute, like MIPS, that was one brand. PowerPC, very popular old Apple systems, and they all got displaced by ARM. ARM never grew as quickly as x86, but it was never displaced. Like, it was like, oh, I have a smaller section of pie, but there were 3 people in the pie, and there's like, now only ARM remained. So brick by brick, ARM started to grow, and open licensing made the massive growth. Basically, the growth in ARM system from early 2000 to 2010, it's bonkers. It's like exponentially more growth compared to what Intel did in 30 years. Because again, there was so much goddamn competition. So I'm talking about like big players. So you have Qualcomm jumping in, MediaTek jumping in, Samsung jumping in, and many, many, many more players. So you are like, bam, 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 bam. People were going YOLO on it. So development in the last 10 years, basically from 2000 to 2010, was like, oh damn, this can actually become a thing. Like, people who knew in the computation industry was like, oh, there is a, like, you know, change on the horizon, so to say. And because more people are opening it, then it created a paradox. It's like, hey, if I'm the one making the goddamn silicon, if I'm the one doing almost everything, why am I paying licensing? So RISC-V was created. Now, let that be very clear. RISC-V is a brainchild of very smart professors. They are like, hey, we need to teach our younglings about instruction set architecture. We can't do Intel because A, it's proprietary, we don't have that. B, ARM, again proprietary, we don't have that. So what can we do? And every time, every semester making up system is not desirable. So they're like, what if we all work together and create a system that just for lol, like, this is how it is, we're gonna create a simulation and all that. And then people are like, hey, it's actually useful. And again, they're like, duh, we are the one who is teaching the one who's doing your work. So it's like, duh, we know our thing. So that started to become an open source thing. Be mindful, it's almost exactly same as Linux. So they started to jump into it. And why people were excited about that? Because so many more people were making hardware. And is slowly gaining popularity simply because there is no royalties. That's why some big people are pouring money into it. Like, what kind of big people we are talking about? We are talking about Amazon, Facebook, Microsoft, Apple, Samsung, MediaTek. So big people are pouring money into it because all of them have in common, they make the damn thing, but they still have to pay royalty to it. And RISC-V has another advantage. It came after ARM. So ARM was quite old at this point in time. So RISC-V had the luxury of like being far more less encrypted, so to say. So they're like, okay, we know what this does. This is why we have it. And people are like, hey, we're not happy with that. Let's remove that module. If you do not need that module, don't put that module. But when you are comparing that to license system, people will pay you license fees if they do not have to deal with headache. So that created them into a cage, so to say. While their cores were really good, it was not as efficient use of silicon as possible, because again, they were locked. And that's why all these companies are working with RISC-V and trying to basically integrate that. And it can be done. It will be done. The small trial runs to testings have already been done, and results are really looking bad for ARM, so to say. Again, early stages, but be mindful, all this happened in less 15 years. So RISC-V is just getting started, so to say. So ARM is also there, RISC-V is also there, and translation of it at this moment in time, as in 2025, the planet has far more compute on RISC architecture than CISC architecture at this point in time. If you're like, okay, we have sold millions of CPU cores, they're like, cool, awesome. Billions of them sold by one company. So fundamentally, there is no scale competition here, because again, Amazon Web Services are not something that are gonna, oh, can you give us 100? No, they're gonna order 10,000 to 50,000 or 100,000 CPU cores, CPUs, physical Xenon CPUs. Losing that is not something like, oh, minor inconvenience. That's like you lose your stock value. And then same goes with Meta, same goes with Amazon Azure, same goes with Mac, same goes with Samsung, same goes with MediaTek. And again, MediaTek and Samsung, they were not that big of a deal, but these were big deals. So almost all in the top 5 companies, they are like, hey, we're going to make our own silicon. So that created a scenario where Intel and AMD randomly started to notice, hey, wait a minute, we are not getting that keep money coming in. The money trucks are no longer coming in. Again, Amazon Web Service alone would be huge. Microsoft Azure alone would be huge. Combine both of them, it's like, whoa, 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 whoa. So this happened. And again, if you had told this thing just few years ago, people were like, nah. Now it's like, damn. It's like people are now, it's like, oh, you're still using x86? And again, these things are not as better as like Epic, Xenoma or things of this nature. It's just that far more logical, far more what you want, and less cumbersome, so to say. So what can we expect in the future? Now, the core word of the future is fluid, meaning everything is now adaptable and changeable. Meaning we have gone are the days like this is how it is written. It's like, nah, bro, we can change it. I'm not even joking. People are changing languages of the software. It's like, well, the software was written in this. Change it, man. We are changing it. And again, our software development kit, the library testing kit, so a lot of things have improved drastically. So this idea was unthinkable, uncalculable in 1990s. Now it's like, yeah, that's a Wednesday. So things have changed. And x86 actually is no longer quote unquote CISC as it used to be, because it has what we call translation engine in the silicon itself. So operating system is talking to the kernel. Kernel is talking to what it thinks is a CISC. CISC is taking that instruction, breaking it apart, and is like, okay, translation engine, do your work. And you're like, wouldn't that have a slowdown? No, the system is ludicrously fast. That's why translation nowadays is not as taxing as it used to be. So, and again, if you have been following your mobile phone, you must have seen back in the days, it used to take time for do any effect on your photos. Now it can be done in real time. It's taking far more computation. But again, because the systems are so efficient and the horsepower is like, it can be done without any issue. And biggest issue for x86 was failed to penetrate mobile market. And again, it's like, oh, 20 years, people have been saying, no. The people who were saying 20 years ago, they noticed that they are failing to penetrate mobile market. And it is starting to yield results right now. The lack of penetration in mobile markets was massive loss of x86. Another aspect is embedded system. They never truly got into embedded systems. They're like, oh, who cares about this sort of embedded system? A lot of people, like billions of them, kind of lot of people. So fundamentally, that's why right now at this point in time you can buy basically ESP32C6 that has a RISC-V core right now. And again, many SSDs right now have from Western Digital has a RISC-6 basically sub processor is from RISC-6 architecture. Pardon me, RISC-V architecture. So that sort of penetration failure in embedded systems and in mobile penetration, that doomed them flat out. And loss of mega enterprise, because they're like, hey, who cares? Like all these are just chump change. That is absolutely true. But yeah, Amazon Web Services is not chump change. That's like massive. Microsoft Azure is not small. They are huge. So those mega customers, losing those enterprise grade customers is like, no, that's like no. And at this point in time, improvement in translation layer makes x86 as just like meh. For example, just in early 2010, if you had said anybody, we're gonna have a Linux handheld and it's gonna play x86 basically Windows game, people were like, yeah, that's not possible. Like flat out, you will not be able to translate that much real time, be fast enough, be responsive enough that it just works. And again, in 2-3 years, it became a reality. Like 3 years ago, if you watch people just talking about this, like, I don't know how they will make it run. Now it's like, it just works. Heck, right now, it's actually better than running Windows itself. So how the heck that happened? Because people realize the fluid is the future. Where it's just like, translate it. Heck, Apple literally did that. It's like, how did they ported the software from x86 to ARM? They did not. They just introduced a Rosetta layer. It's like translation. And again, if company was wise enough, they did do some bug fixing and all that and do some baking and testing, but it made sure that at least that initial impossible is like minor inconvenience, impossible to minor inconvenience. And again, how good the translation layers are becoming, I can easily see if Steam keeps working at it, in 3 to 4 years time, people will be like, hey, if you want to play a game, use Steam OS. It literally would be better, assuming that anti-cheat software is sorted. So that happened. Why? Because translation layer. And here's the, what if they decide to, instead of using AMD's x86 CPU, they're like, hey, what if we eat that? Now, would the software support it? Of course, because it's Linux. They can easily port it. The kernel is more than comfortable to talk with ARM systems. And you're like, okay, what about the games and all that? Games do not want anything. They just talk. So translation layer is like, what do you want? Oh, you blah, 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 blah. Okay. Hey, can you render this triangle and send it the data? That's what happens. That's the translation layer job. It's like what they are saying versus what the hardware can do. Translate it quickly enough and like, make it efficient enough. It just works. And inherently, you also have to understand all the software drivers, they are translation inherently. So fundamentally, if x86 does not do something great, they can fade. Because again, these people are running away from x86. That's bad. Again, I can easily see them where it's like, hey, x86 was good. We solved all the software issues. Now we can trust our system. What if we jumped from x86 to ARM? It would not be a massive jump. It will be like, huh, we could do it. Oh, fun fact. NVIDIA, their current supercomputers that they are selling for massive AIs, all of them have their own in-house silicon running with ARM or RISC architecture. Now, some of them are also experimenting with the RISC-V, so that's there. So inherently, x86 is almost in a rough spot, so to say, because I do not think it's even remotely possible for them to touch embedded systems or penetrate mobile anymore. So, and again, once you lose those mega players, once they are like, hey, we built our own silicon, we built our own stack, we know everything from start to finish, why would we pay? So, and again, the miserable performance of Windows on x86 hardware pisses everybody off. And again, it's more of the Windows fault, but again, people will say I could use ARM systems. So x86 has to really fix themselves. Failure to do so, in 10 to 15 years from now, it will be like gone, exactly like PowerPC. So this was my presentation on basically what is the future of x86. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.